Synaptics, yay. Okay, synaptics. All right, that works. Share that. Come on. So please remember, this is not open seating. You are supposed to try to stick with your seat, right? And if you do move, please try to let me know. We don't want conflicts, at least until they give us the all clear, which I hope they will at the end of September, maybe. It's a reasonable possibility that we might be able to relax a lot of this nonsense by then. But until then, try to stick with what we've got. Okay, so if you are joining us on the Zoom, please be sure to type something in the chat box that will record your attendance. And if you are here in person, please sign in either at the front or at the front or at the back or at the back. There's 4 sign-in sheets so that nobody has to get crowded. All right, that's how I establish your attendance. And attendance plus being embarrassed in front of the whole class once or twice a semester counts for a whole exam. So please be sure to sign in. If you haven't signed in now, be sure you do it before you leave. Okay. So let's see where we are here. So today we are going to start trying to lay out the groundwork for adaptation to the environment. In order to do that, we have to know something about the environments we're talking about. The environments we're talking about here are generated by the large-scale weather patterns that we find on Earth. So this will be something of a meteorology lecture. Just think of me as Margaret Orr, even though she has more hair than I do. But we will work through how the big patterns of climate are established on the face of the Earth, and we will then work through their consequences in coming lectures until we get to actually enumerating the kinds of adaptations that organisms have to have. Okay. So first, today we're going to cover 5 topics, and that's the heating of the Earth by the sun, which is greater at the equator than the poles. We're going to examine how that generates these large-scale circulation cells in the atmosphere, which are the key to pretty much everything. And then we'll talk a little bit about physics. We'll talk a little bit about the properties of air, pressure, heat capacity, moisture holding potential, things like that, and how they generate global precipitation patterns. Then we'll look at the seasonal shifts in these air circulation cells that generate our seasons. And finally, we'll deal with the most difficult thing in the lecture, which is the Coriolis Force. How many of you have been on a merry-go-round? Let's see. Right. Okay, well, good. So some of you will have some basis for understanding what we're trying to do here. Maybe not a lot, but a little. Okay, so to start with, then, the entire heat budget of the Earth comes from the sun. And the thing is that that heat budget is distributed unequally on the face of the Earth. There's a greater amount of solar radiation that hits the ground in any given unit of area at the equator than at the pole. And there are three reasons why that is. First, solar radiation travels further through the atmosphere at the poles than it does the equator. That gives air molecules more opportunities to absorb or scatter sunlight. The path to the Earth's surface is much more direct and shorter at the equator. That means there are fewer opportunities for solar radiation to be deflected or absorbed. So it gets to the Earth's surface more effectively. Second, the angle at which solar radiation hits the Earth is quite different. At the equator, perpendicular. At the poles, slanted. Okay, and all you got to do is take a piece of plywood at home, hold it upright, shine a flashlight on it, trace the area that it illuminates, and then slant it. Hold that same flashlight at the same distance, and you'll wind up tracing a much larger area. Okay, third is the albedo of the Earth at any given location. The albedo is the light reflecting ability of substances. Objects with a high albedo reflect a lot of light. With a low albedo, they absorb a lot of light. Okay, so if they're absorbing the heat energy of that photon. If they're reflecting, they're just bouncing it right back. So let's look at how these things work together. So first, let's look at the distance. All right, we already said less solar energy is absorbed or scattered at the equator than at the poles, and more of it actually strikes the ground, where it is absorbed, warming the ground. Okay, and here is an illustration of that slanting of the Earth's surface towards the poles versus the perpendicular arrangement of the Earth's surface to the sun at the equator. And so here you see, there you go. The Earth's surface is heated more at the equator for this reason also. And let me see if I can do this. So I'm going to use the cursor for the benefit of the people at home. We're talking about this oblique angle here at the poles and the perpendicular here at the equator. And I hope you all can see that. I do have a pen to write on, but I don't think it's necessary for this. Okay, third is the albedo, right? So that's the reflectance of objects. So here, if you have high albedo, you've got a light colored surface, and that's reflective. Dark colored surfaces have low albedo. And here's a comparison of the albedo of a number of kinds of surfaces. So snow, very high albedo, reflects a lot of solar energy and absorbs almost none. Okay, sea ice is also very high albedo. On the other hand, open water has a much lower albedo. Open ocean absorbs most of the energy in solar radiation that hits it. And terrestrial kinds of lands are, they vary quite a bit. Forests absorb a lot, crops absorb a lot. But here's asphalt. Asphalt absorbs by far the most. Okay, what are cities mostly? Asphalt. That's why we have the urban heat island effect. The more trees you have in a city, the lower, the higher the albedo, and the lower the heating is. If you have a lot of asphalt, on the other hand, that area is going to heat up. So it's a good thing to have trees in cities rather than asphalt. And if you can't have trees, it's good to have grass rather than asphalt. So there's a lesson for city planning for you all. Now, as a result, there is a global temperature gradient from warm at the equator to cool at the poles. Okay, and you see that there's kind of an imbalance here because the South Pole is actually colder. That's because of the very large ice cap, whereas the North Pole has a seasonal ice cap. South Pole has a permanent ice cap that's roughly 2 to 3 miles thick. Okay, so that's why we have weather. This gradient then promotes particular patterns of heating and cooling of air, and that generates the big circulation patterns that we see on Earth. So let's examine how that works. And what do I mean exactly by 6 large-scale air circulation cells? Well, one way to think about this is if the Earth is a ball, think of 6 donuts that surround that ball. So when I give you a 2-dimensional diagram, what I want you to be thinking about is a 3-dimensional Earth with not a little circle, but a ring, like a donut, as we go through this. So let's just examine how solar heating does this. Remember, we have the maximum heating of land and water occurring at the equator. That heats the air above the land and water because water has a very high thermal capacity. Air has a very low thermal capacity. It heats up and cools down very quickly. So a little bit of heating of water can heat the air around that water a lot. Hot air quickly produces, or hot water quickly produces hot air. Land has slightly lower heat capacity, but it also has a much higher heat capacity than air. So warming the Earth's surface also warms the air above it very quickly. And what happens with warm air? It rises. So at the equator, you have a column of rising air. And of course, it's not a column, it's a belt that surrounds the entire Earth's surface. So try to think in 3 dimensions as we talk in 2. So that air rises from the Earth's surface into the high atmosphere. And then it goes out into outer space and winds up on Venus somewhere. No, actually it doesn't, because it can't. There are temperature discontinuities in the atmosphere that prevent that. In fact, there is a temperature discontinuity called the Tropopause, where there is a sudden drop in air temperature high above the Earth's surface. And we're talking about a drop of, say, 100 degrees centigrade. Okay, well, that puts a cap on how far air is able to rise from the Earth's surface. It acts just as if it was a lid, and it prevents it from rising any further. So it's rising, it hits the lid, it's moving, it can't go up. What happens to it? It circulates away from the equator, either north or south. Why can't it move east or west? Let's do some 3-dimensional thinking here. Melina, are you here today? Why can't it go east or west? Think 3-dimensionally. Yes, that's exactly right. So the hot air is rising to the east and the west also. It's not a two-dimensional diagram. It's a three-dimensional belt that covers the entire Earth. It's a curtain of rising air that covers the entire equator all around the Earth. So the only way it can go is north or south, away from the equator. So now it's going to move north or south. It's at the top of the atmosphere. It's adjacent to extraordinarily cold temperatures. Okay, this is warm air, right? What happens when you put a warm thing against a cold thing? What happens to the warm thing? It loses its heat, right? It radiates its heat to space. So as this air moves away from the equator, it is constantly radiating heat into space and cooling. Eventually, it cools enough that it starts to sink. Okay, and that's because warm air has low density, cold air has high density. Let's think about what temperature actually means. Temperature is simply the collisions between molecules. Warm air means active molecules, lots of collisions, but that means they're bouncing off each other and they're spreading out. So warm air is low density air. On the other hand, cold air has many fewer and less energetic collisions between air particles, and that means that they're jam-packed closer together. So density of cold air is high. Yes? Okay, the question is, and I forgot to do this last time, but I'll do it from now on. The question is that's why it's harder to breathe at, say, high elevations. Yes, that is a reflection of the lower density of air. And quite specifically, it's the loss of oxygen concentration as that air gets less dense. The concentration of, well, it's not the concentration, it's the, I guess it be equivalent to like the vapor density of oxygen at sea level is about 20.8%. If you get up to 14,000 feet on one of the high mountains in the contiguous United States, it drops down to 17 or 18%. So it's the equivalent of a much lower oxygen concentration. But that's because the oxygen molecules are spread much further apart, and as you take a breath in, you get less oxygen. Okay. So we have rising air at the equator as that air is heated by solar radiation. It is capped off at the tropopause. It moves north and south, losing energy to space, eventually becomes dense and sinks back to the Earth's surface. Now, this then is going to sink to the Earth's surface and it can't go anywhere, so where does it go? It once again has to go either toward the equator or away from the equator. It cannot go east or west because there are similar columns of falling air to the east and to the west. The only way for this air to go is towards the equator or away from the equator. And you see we've got both of them diagrammed here. The air that returns to the equator here basically then produces a circulation cell. That's called the Hadley cell after the meteorologist who first described it. So here's our first set of circulation cells. These are tropical circulation cells between about the equator and 30 degrees north and south. Yes. We're getting to that. We have not gotten to the feral cell yet. Not a bad way to think about it. He's asking, for those of you at home, is it circulating like an infinity sign? Sort of. It's not a bad way to think about it. So we'll move on and show you exactly how it works now. Okay, so here's our circulation cell. We've talked about the air that hits the Earth's surface and moves back towards the equator. What about the air that moves away from the equator? Well, it's moving across land. And remember, this has been cooled up here at the Tropopause, and now it's moving along the Earth's surface, which is absorbing heat. And because of the higher heat capacity of the Earth's surface compared to air, that air is going to pick up heat once again. As it moves north and south away from the equator, it will eventually pick up enough heat that it becomes less dense and it rises once again. And of course, it's going to hit the tropopause again. It can't escape the tropopause. So once again, it's going to spread out north and south towards the equator, away from the equator. And here you can see that it's rising here. It's rising here. If it moves back towards the equator, well, it's now completed a second set of circulation cells, the feral cells. These are the temperate cells. Okay? The latitude at which you typically get this rising column of air is somewhere around 55 to 65 degrees. On average, it's about 60 degrees. This is the area, by the way, where the jet stream tends to run between the Arctic and temperate areas. Okay, so we have air moving towards the equator or away from the equator in the feral cell. Also at the tropopause, clearly, if it's moving away from the equator, it's headed toward the pole. Okay, now the poles are the coldest areas on Earth. You're losing energy to space. Eventually, this air cools enough so that it sinks once again over the poles, forming the last set, the polar cell. Okay, so we have rising air at the equator and at 60 degrees. We have sinking air at 30 degrees and 90 degrees. So, how are we doing? Does anybody have a question? Okay. I don't see a question from home, so I'm going to move on. Now, let's then look at how these movements of air generate precipitation patterns. All right, as air temperature increases, it can hold greater amounts of water. Cold air can only hold a small amount of water. Warm air can hold quite a lot of water. So here is the saturation curve of air at different temperatures, right? And it's kind of an rising curve. It's this thing right here for those of you at home, this curve here, right? Now, if you have more water in the air than it can hold, it condenses and falls as rain. If the air can hold more water than it currently has, it absorbs water from anything around it. So if you have a warm, dry air mass sitting over the ocean, it has the ability to suck up enormous amounts of moisture. If you have an air mass that cools off, it's going to rain because the amount of air that it can contain decreases as the temperature drops. So the amount of moisture has to drop from this level to this level if it cools. Yes. I'm sorry, louder. Okay, fog is, the question is, how do we get fog if we're not raining? Fog is a phenomenon that occurs when you don't have sufficiently large nuclei to cause rain, and also when the difference in temperature occurs close to the ground surface, all right? So if you have a warm body of water next to a cold landmass, and you get the wind blowing from the ocean to the land, some of that water will condense. But it's not high enough in the atmosphere to really fall as rain. It's just going to be foggy. Uh, you're asking a question after my own heart because I grew up in San Francisco, which is, of course, foggy. Okay, so the key thing to remember here is that if air is warm, it's going to absorb water from what's around it. If it cools, it will lose the water that it already carries. So let's see how pressure then affects the temperature, which then affects the moisture that air can contain. At the Earth's surface, you have the entire column of the atmosphere pressing down. So you have very high pressure at the Earth's surface. As you go up towards outer space, you have less and less atmosphere pressing down. You have lower and lower densities. That means lower pressure. They have high pressure at the Earth's surface, low pressure high up. Well, if you have high pressure, you're compressing the air. You're making those molecules bang on each other much more because they're closer together. So it's warmer. High pressure at the Earth's surface produces warmer air than low pressure high in the atmosphere. That produces cold air. Okay, if you're heating and cooling because of temperature, we call this adiabatic heating or cooling. So you get adiabatic cooling if you have air that gradually experiences less and less pressure. That allows the air molecules to expand. They interact with each other less, becomes less dense. It cools because the movement of the air molecules is not as great. On the other hand, if you have air that is compressed, you are causing the air molecules to interact with each other more and more and more. That's heat. So that's adiabatic heating. The key thing about precipitation on Earth is that it is due to either adiabatic heating or adiabatic cooling at its core. So let's examine what happens at the equator. We just said there's a column of rising air, right? At the equator because of the heating from the Earth's surface. Well, okay, so you have this warm air. Well, that air is warming as it passes over the land, absorbing solar radiation. As it warms, what happens to its ability to hold water? It increases. So this warm air near the equator is capable of absorbing enormous volumes of water. Yes. Yes, that is right. Yeah. Hurricanes get their strength by absorbing massive volumes of water. As they pass from ocean to land, the amount of moisture that they can absorb decreases, and they lose strength as a result of that. I'm glad you asked that question about hurricanes, because at the end of class, we're going to establish a relationship between this fan and hurricanes. There we go. It's kind of loud, so I'm not going to leave it on. All right, so we have hot air at the equator. It's absorbing enormous amounts of water, and then what happens to it? You had a question? Hurricanes, the question is that why hurricanes strengthen when they're over warm water? That's exactly right, because the warmer water allows more evaporation, and that allows the air to pick up more energy from the ocean. So yes, that is why hurricanes strengthen like that. So we've got this hot air full of water. What happens to it? It gets less dense because it's being heated, and it rises. Well, what happens to the pressure in the atmosphere as it rises from the Earth's surface to the tropopause? It decreases. The pressure decreases, allowing that air to expand. And what's the relationship between the density of air and its temperature? Expanding air is cooling air. So, as this hot, wet air at the equator, which we see in number 1 here, rises high into the atmosphere, there's 1, rises as 2, it cools and loses its ability to hold that moisture. That moisture then falls as rain. That's why the tropics are wet. Okay? As it hits the tropopause, it's been wrung out of all the moisture, so now it's not just cold, it's dry. Really dry air. As it moves away from the equator towards the poles, it's losing more and more heat, not gaining any water, right? Eventually it sinks, but now it's sinking from an area of low pressure into an area of high pressure. What happens to the temperature? It increases. So you have extremely dry air that is heating up and getting more ability to absorb water. And what it does is then absorb water from the land under it as it falls back to the Earth's surface. So we think of deserts as being associated with hot air, but we often think of it backwards. It's the falling mass of air that is heating up and gaining the ability to hold more water that causes deserts. Deserts don't cause hot air. Hot air causes deserts. Having this sinking air column here, which is kind of 5 on this diagram for those of you at home, having that sinking air column is like pointing a blow dryer at the Earth's surface. It's sucking all the moisture out of the Earth's surface because that hot air has a tremendous capacity to absorb moisture. So look, we just explained 2/3 of the Earth's surface here. We've explained why the tropics has moist rainforest type habitats, and we've explained the belts of deserts at 30 degrees. All right, so we mentioned that we have these 6 circulation cells, 3 in the northern hemisphere, 3 in the southern hemisphere. Anytime you have rising air, you're going to have a precipitation belt. So not only do we have a precipitation belt at the equator, where else do we have it? Right there, 60 degrees north and 60 degrees south, where the other columns of rising air occur on Earth. Those are areas of rich precipitation. Anytime you have sinking air, you have deserts, because that sinking air is warming as it hits the Earth's surface under high pressure. Adiabatic warming then allows that warmer air to suck moisture from the Earth's surface. So you have deserts under falling air columns right here at 30 degrees and at poles. The poles are, in fact, cold deserts. You may only have 5 centimeters of precipitation a year at the poles. Thing is, it doesn't melt, it accumulates. But the poles are functionally deserts in terms of precipitation. They're under areas of falling air that is warming up, that is sucking moisture from the land around it. And now we know why we have big types of habitats in particular areas on the Earth's surface. Okay, I'm going to stop and ask for questions at this point. Yes. Ah. Well, okay, so the question is that why it's dangerous when it does rain in a desert? That has actually much more to do with the lack of anything growing in the desert that can buffer the large amount of rain from running off instantly. So another place that I've lived is Phoenix, Arizona. And there just isn't enough vegetation to absorb heavy rain. So it simply runs off. It causes flash flooding. But that's an outcome. All right, let's move then to the seasonal. Oh, yeah, we have another question. Okay, so why is that explain why it is cold in the desert at night? It has more to do with the fact that falling air absorbing moisture then takes it away and from a particular location. What that means is that the falling air itself has very little water vapor in it. And if you think about what clouds are, well, that's just water vapor. So deserts are cold at night primarily because they tend to be cloudless more than other kinds of areas. So it's related, not exactly the way you were thinking, but it's related, yes. All right, let's look at the seasonal patterns then. And here we go. We know that our Earth's axis is tilted by 23 degrees. That means that we present different hemispheres to the sun at different times of year. In fact, I've been kind of lying to you when I say that the heating is maximum at the equator. That's true only twice a year, right? When in fact, at March 20th and September 20th, the equator is actually directly facing the sun. At any other time of year, the area of intensive heating is actually a bit north or a bit south of the geographic equator. And that's because of this tilt. So here you can see this is the northern summer here. And the area that is facing the sun is north of the geographic equator. In the northern winter, the area that's facing most directly the sun is south of the geographic equator. All right, well, those circulation cells that we diagrammed are not tied to the geographic equator, they're tied to the solar equator. So the area of maximum heating and maximum rainfall in the tropics moves into the northern hemisphere in the summer, in our summer, and into the southern hemisphere in our winter. Those circulation cells basically are oriented by the solar equator, not the geographic equator. All right. And what that means is that the solar equator, which moves between 23 north and south, more or less, the Tropic of Cancer and the Tropic of Capricorn, that determines the orientation of those 6 circulation cells and gives us our seasonal change in weather. Okay, so let's look at what happens to that area of maximum heating over the course of a year. All right, well, this is the equator here, the geographic equator. Here's Bogota, lovely town. And here's Rio de Janeiro down in the south, and here's Merida close to the northernmost excursion of the solar equator. And what you see is the area of maximum heating and highest rainfall moves north and south. Okay, so in the southern summer, it's down here. As we move from the southern summer to the equinox in spring or fall, it moves towards the equator and crosses the equator in March or September. Then in the northern summer between March and September, we have the maximum heating and maximum rainfall in the northern hemisphere. In September, that solar equator moves south of the geographic equator, and we get that area moving south again. All right, well, look at what that means here. On the equator, you get 2 rainy seasons a year. If you're north of the equator or south of the equator in the tropics, you get 1 rainy season. And that will have consequences when we talk about the distribution of biomes in 2 lectures. Okay, so this area of maximum heating or heating and rainfall is called the Intertropical Convergence Zone, the ITCZ, and this traces its movements over the course of a year. Okay, and let's then look at the more general picture of how the circulation cells move. In the northern summer, here's the northern solar equator here. And look, the Hadley cells have moved into the northern hemisphere. In the southern summer, those Hadley cells have moved into the southern hemisphere. And twice a year, they are exactly oriented over the geographic equator. Now, the interesting thing about this is that there's a lag. There's a lag time. So you'd think possibly that the heating and cooling would exactly match the march of the season. In fact, it's delayed. Why is that? Because as you have the intertropical convergence zone moving north in the summer, in the northern summer, it's been heating this area, right? It's been heating this area. It hasn't been heating this as much. So the actual position of the intertropical convergence zone kind of lags behind the movement of the solar equator. Here we are in the northern summer, and you can see that the Hadley cells are quite far north. As the sun begins its southward movement, it's been heating this area in the northern hemisphere for quite a long time. And that intertropical convergence zone doesn't immediately move south. There's a lag. This northern area has to cool off a bit before the area of maximum heating actually moves south. So although we define the seasons in terms of days of the year, the intertropical convergence zone and the pattern of actual movement here lags behind. And if you think about it, the area of maximum heating is in the northern hemisphere. The solar equator is in the northern hemisphere from March to September. Okay, but hurricanes are generated by heat. When's hurricane season? It's not March through September. It's lagging. It's lagging because the maximum area of heating is lagging. You don't really warm up enough in the northern hemisphere until later in the year, usually June. Okay, and you stay warm a little bit longer than you'd expect. You don't lose the hurricane season in September, you lose it in November. That's a good illustration of the effect of having this lag. All right, so last thing we're going to do is the Coriolis Force. Now, I want you to think about this air circulation cell. Keep that in your mind, right? I want you to realize that New Orleans is right about here, just above that dotted line, the Tropic of Cancer, because that will have some consequences. All right, the Coriolis Force. Coriolis Force is generated by centrifugal force. The Earth is rotating, right? And it's rotating at different speeds, depending on where you are on the face of the Earth. The day is 24 hours long. The Earth is 24,000 miles in circumference. That means that at the equator, the rotation is 1,000 miles an hour. What is the rotation at the poles? It's 0. All you're doing at the poles is standing in one place and turning around in a circle, right? You're doing this. But you're moving at 1,000 miles an hour at the equator. Well, that has some consequences, okay? If you think about it, if you've been on a merry-go-round, if you ever close your eyes and try to walk from the center to the edge, you have to close your eyes to do this. It doesn't work if your eyes are open. But if you close your, and of course you're going to run into something. But if you were to do that, you would think that you would walk a straight line, right? But in fact, you're not, because the base of the merry-go-round is turning under you as you walk. So if it's turning from my right to my left, I close my eyes and I think I'm taking a step straight out. I'm not, because the merry-go-round has turned under me. So instead of stepping straight out, I turn slightly to the right. I'm not doing anything. I'm moving straight. It's the merry-go-round moving under me that generates that apparent motion. That's the principle we're talking about here, the apparent motion. And the difference in apparent motion that is generated by the differing rotation speeds on the face of the Earth helps explain why winds blow from east to west or west to east, but not north to south. So let's try to unpack this little diagram. So we've got the Hadley cells here, right? And we're just going to, for instance, put them on the geographic equator for simplicity. The air at the Earth's surface under the Hadley cells is moving towards the equator. But where's it moving from? It's moving from an area that's rotating at about 700 miles an hour to an area that's moving 1,000 miles an hour. So the Earth is rotating from west to east under the wind. And because of that, it feels like the wind is coming from the east. The wind is not coming from the east, it's coming from the north and the south. You're just on something that's rotating under the wind. Let me ask you, when you stick your head out a car window, which direction is the wind coming from? From the front. It does not matter where the wind is actually coming from, because you are almost always moving faster than the wind. The apparent motion is what you perceive. Okay, so that's easy to understand. But the thing is, if you're here at 30 degrees north and the air is moving away from the equator, you're moving from an area where you're rotating at 700 miles an hour into an area where you're only rotating maybe 300 miles an hour. So the wind is moving faster than the Earth's surface, and it overtakes the Earth's surface from the west. These winds are actually blowing directly north and directly south, but the difference in apparent motion makes them appear to twist. Between 30 degrees in the equator, the Earth's surface is moving faster than the wind blowing over it, and it appears to come from the east. From 30 to 60, the wind is blowing faster than the Earth's surface, and it appears to come from the west. From 60 to the poles, once again, the Earth's surface is rotating faster than the wind, and it appears to come from the east. Okay, and with that, I will ask, who will I ask? Danny, are you here? Yeah, come here. All right, Danny, come here. Stop right there. Which direction is the wind blowing? Yeah, it's blowing that. Okay, now stand over here and walk at 1,000 miles an hour this way. Which way is the wind blowing? Yeah. Okay, the wind is not blowing in his face. The wind is blowing directly across his body. But his apparent motion is faster than the wind. So it feels just exactly like sticking your head out a car window. The wind is always coming from the east between 30 and the equator. It's always coming from the west between 30 and 60. And of course, that has some consequences for us because when's hurricane season? Okay, and where's the Hadley Cell at that time of year? Let's go back and look at that. Where's the Hadley Cell? The Hadley Cell is here. And so that wind is twisting out of which direction? The wind is twisting out of the east. We don't have hurricanes all year long because we are exactly at 30 degrees. In the northern summer, those Hadley cells are over us and the wind is blowing from the east, from Africa to us. But in the winter, the Hadley cells move south. The Ferrel cells are over us and the wind is blowing from the west. It's blowing from New Orleans to Africa. We don't get hurricanes. Okay, so El Nino, La Nina, the El Nino Southern Oscillation, ENSO, affects the strength of these winds. Okay, and it affects the exact positions of those circulation cells. So that's why in El Nino years, we don't get as many hurricanes because it's harder for them to form, harder for them to move. The winds are weaker.
Dr. Howard, can you hear me? Dr. Howard?
Hang on, yeah, Laura?
So the jet stream, is that part of the westerlies or is that a lower level wind?
Okay, the jet stream generally, let me use the cursor, jet stream generally occupies this kind of interface between the polar and westerly winds, and it's not a regular thing. It swoops and swirls. So it's not actually necessarily a part of the westerlies as we think of them. It's really a high altitude thing that is separate from the surface wind that you see here. Okay. All right, so El Nino, La Nina is a global phenomenon that affects the strength of these winds. And El Nino years, we have fewer storms because the winds are weaker. La Nina years, we have more storms because the winds are a bit stronger. They're not necessarily opposing one another. By the way, we're done for today, so we're just cleaning up here. By the way, Danny, thank you. You get a point for being humiliated. Okay, guys, this is it for today.
Hey, Dr. Howard, I also have a question for the